close your eyes for a moment and picture the Earth as it looked about 252 million years ago. The continents had drifted together into a single vast landmass called Pangea. Around it stretched one enormous ocean called Panthalassa, calm and blue and warm at the surface. From far above, the planet would have looked familiar, and yet entirely strange. One supercontinent, one sea, one world about to fall almost completely silent. This is the story of the largest extinction event the Earth has ever known. Scientists call it the Permian Triassic extinction. Some call it the Great Dying. In a window of geological time that may have lasted only a few tens of thousands of years, somewhere near 9 out of every 10 species on Earth simply vanished. In the oceans, the loss may have reached 96%. On land, whole groups of insects, plants and reptiles disappeared and never returned. The fossil record, normally so full of small details, goes quiet. Layer by layer, the stones grow empty, and here is the soft, strange truth at the heart of this episode. We still do not fully know why it happened. We have theories, many of them. We have evidence carved into ancient rock, from Siberia to South Africa to the cliffs of southern China. We have chemical fingerprints in stone and bone. But the picture is not yet whole. Researchers continue to argue about the order of events, the speed of the collapse, and the deepest cause. The mystery is genuine. The question is still open. Before we go further, the planet has a new quiet wonder to share every night. If you'd like, one waiting for you each evening, subscribe and let it come to you. For tonight, simply sit with the scale of it. Imagine standing on the shore of that single great ocean. Near the end of the Permian period, the air is warm. The light has a slightly hazy quality, as if filtered through soft smoke behind you. The land rolls inward across thousands of miles, dry in places, swampy in others, dotted with low forests of seed ferns and tall, scaly trees whose names belong only to deep time. Strange reptiles move slowly through the underbrush. Some look like heavy, barrel-chested pigs. Others are long and lizard-like, with tusks or beaks, or rows of small, sharp teeth. In the sea behind you, the water is alive. Coral-like animals build wide, flat reefs in the shallows. Spiral-shelled creatures called ammonoids drift through the deeper blue. Small, lampshade-shaped animals called brachiopods sit in vast beds on the seafloor. Trilobites, those gentle armored wanderers that had survived for nearly 300 million years, are still here, though their numbers have grown thin. The world is full and crowded and old, and then, slowly at first, something begins to change. Far to the north, in the region we now call Siberia, the ground itself opens. Lava begins to pour from cracks in the crust, not in one quick burst, but in waves over thousands upon thousands of years. The eruptions release rivers of basalt across an area larger than many modern countries. Along with the lava comes gas, carbon dioxide, sulfur, methane, and other compounds that drift up into the sky and settle into the sea. What followed is the part we are still trying to read. One theory says the air grew hot and thick, the oceans warmed, and the deep water lost its oxygen until vast regions of the sea became suffocating and still. Another theory adds that the water turned acidic, dissolving the shells of small creatures before they could grow. Some researchers wonder whether a distant impact, a comet or asteroid, may have helped to push the dying world over its final edge. Others see only the long, patient work of the volcanoes themselves. The evidence supports parts of each idea. None of them alone seems to explain everything. That is why this episode is built around a question rather than an answer. Across the next few hours, we will walk slowly through the world, before, during, and after this great quieting. We will look at the rock layers that record it. We will listen for the survivors, the few small lineages that lived through the long, empty Triassic dawn. We will sit with the parts that remain unknown. For now, picture that single warm sea, that one great continent, and the soft sound of waves under a sky that is just beginning to change. The world has almost ended before, and somehow, life has always found a way to begin again. Why it nearly ended that one time, more than any other, is the gentle puzzle we will hold tonight. To understand what almost ended life on Earth, we first have to understand how anyone could possibly know about it. The event happened about 252 million years ago. That number is so large it slips past the mind without leaving a mark. So let us slow down and make it real. If every year were a single grain of fine white sand, the time since the extinction would fill a small bathtub, not a swimming pool, not a lake, a bathtub. And yet within that bathtub of sand, every grain is longer than a human lifetime. The way we read this deep time is through rock, layered rock specifically. Imagine a tall cliff at the edge of a quiet desert canyon, glowing soft orange in the lake light. Look closely and you will see stripes. Some stripes are pale and chalky, some are dark and crumbling, some are reddish, like rust. Each stripe is a page. Each page is a slow record of one slice of time, pressed flat under the weight of everything that came after. Geologists call these layers strata. Stratum simply means a sheet or a bed. Stack enough sheets and you get a book. The oldest pages sit at the bottom. The newest pages sit on top. This simple idea, that lower is older, is the foundation of nearly everything we know about the deep past. The book is not always neat. Sometimes pages are missing. Sometimes the book has been folded, tilted, or even turned upside down by the slow shifting of continents. But with patience and many books from many places, the story can be pieced together. Inside each layer, tiny clues are sealed. Fossils, of course. The stone outlines of shells, bones, leaves and burrows. But also chemical clues. The exact mix of elements in a layer can hint at the temperature of the ancient ocean, or the gases in the ancient air. Even the magnetic direction frozen into certain minerals can tell us where the rock was sitting when it formed. A single thin band of clay, no thicker than your finger, can hold a whole chapter of Earth's history. The pages that record the Great Extinction sit at a special place in the book. Geologists call it the Permian-Triassic boundary. The Permian was the period before. The Triassic was the period after. The line between them is not always sharp. Sometimes it is a soft blur. Sometimes it is a strange dark layer that looks oddly empty. In a few famous cliffs in southern China, you can stand with one hand on Permian rock and the other on Triassic rock, with only a few centimeters between your palms. Those few centimeters hold the disappearance of perhaps 90% of all species on Earth. That number deserves a pause, 90%. If you imagine 100 different living things, 100 kinds of fish, insects, plants, reptiles, worms, corals, only about 10 of those 100 made it through. The rest left only their shapes in stone. No other event in the long history of complex life came so close to wiping the slate clean. How do we know it was 90% and not, say, 50? This is where the mystery begins to creep in, even at the level of basic facts. The number is an estimate. It comes from counting fossils in many places around the world, before and after the boundary. and seeing how many forms vanish. But fossils are rare. Soft creatures rarely leave a trace. Whole habitats may have left no record at all. So the true figure could be higher, or it could be a little lower. Most careful estimates settle near 90% of marine species and around 70% of land vertebrates. But the edges of those numbers are still gently debated. The age itself, 252 million years, comes from radiometric dating. Certain minerals contain tiny amounts of radioactive elements that decay at a known steady rate. Measure how much has decayed, and you can read the age of the mineral like a very slow clock. Different labs, different methods, different rocks, and yet they all cluster near the same date. That agreement is part of what makes us confident the event was real, and roughly when it happened. What we still do not fully know is what those silent pages contain in their finest detail. The clay band, the chemistry shift, the missing fossils, each one whispers a different part of the story, and the whispers do not always agree. So we read carefully, page by page, knowing that the book is patient. It has waited 250 million years already. It can wait a little longer for us to understand. To understand what was lost, we have to walk gently back into the world that came before. Long before the Great Dying, Earth wore a very different face. The continents had drifted together over many millions of years, slowly pressing themselves into a single vast landmass we now call Pangea. Imagine one giant continent stretching from pole to pole, surrounded by a single huge ocean called Panthalassa. The shape of the planet, seen from above, would have looked almost unrecognizable to us tonight. This was the late Permian period, roughly 260 million years ago. The world had been settling into a long, quiet rhythm. The wild swings of earlier ages had softened. Climates had grown warm and stable across much of the planet. In many places, the air was thick and humid, and the days passed under skies that shifted slowly from pale gold to deep blue. The interior of Pangea, far from any sea, was a vast, dry region of red sands and baking rock. Some scientists picture it as a quiet desert, stretching for thousands of miles, broken only by the occasional dry riverbed or salt flat. The colors there would have been soft and rusted, with long shadows in the morning and evening. No grass grew on those plains, because grasses had not yet appeared on Earth. The ground was simply bare stone, sand, and sometimes low mats of moss and lichen, clinging to the damp corners. Closer to the coasts, the picture changed. Warm rains drifted in from the great ocean, feeding belts of forest that ringed the continent. These forests were nothing like the woods we know today. There were no flowering trees, no oaks, no maples, no birds singing in the branches. Instead, tall seed ferns spread their feathery fronds toward the sun. Strange kern-bearing trees stood in groves, and primitive relatives of conifers stretched their needled limbs into the warm, wet air. The seas, meanwhile, were full and busy. Shallow tropical waters lapped at the edges of Pangea, and these shallows teemed with life. Reefs rose from the seabed, but they were not built by the corals we recognize now. They were made by sponges, by strange tube-shaped creatures, and by ancient relatives of corals long since gone. The reefs glowed in pale yellows and soft pinks, and small fish darted through their corridors. The open ocean held its own quiet wonders. Schools of armored fish moved through the water on slow, patient currents. Sharks of unusual shape, some with strange spiral teeth, glided along the deeper edges. On the seabed crawled trilobites, those small, segmented creatures whose long story was already nearing its final chapter. Crinoids, sometimes called sea lilies, swayed in dense underwater meadows, their feathery arms straining the water for food. On the land, life had also grown bold and varied. Early relatives of mammals, called synapsids, moved through the forests and across the plains. Some were heavy and slow, with thick legs and broad jaws. Others were small and quick, perhaps hunting insects in the leaf litter. There were lizards and amphibians too, and great hulking creatures whose names we have only learned through their bones. None of them ruled the world the way later dinosaurs would. They simply shared it. How exactly all of this came to be is still being pieced together. The slow drift of the continents into Pangea took hundreds of millions of years. Older mountain ranges were worn flat by wind and rain. New ones rose where the continents pressed against each other. The climate shifted as the shape of the world shifted, and life adapted at its own slow pace. Some researchers think the merging of the continents itself set the stage for what came later by changing ocean currents and rainfall patterns in ways we still struggle to model. What we can say is that the Permian world had taken a very long time to grow into the shape it held. Tens of millions of years of relative calm had built up rich ecosystems on land and in the seas. The diversity was real, the balance was deep, and the rhythms of life seemed steady to anyone walking the warm shores of Pangea. The world would have felt permanent, stable, old in the best sense. We know now that this calm was not the whole story. Beneath the quiet forests, beneath the warm, shallow seas, slow forces were already moving. Heat was gathering deep in the mantle. Pressures were building in places no living thing could see. The world before the storm looked timeless, but it was already changing in ways the creatures of that long afternoon could never have understood. Before we can understand what was lost, we have to picture what was living. And the seas of the late Permian held creatures so strange that if you saw them today, you might think you were dreaming. They were not dinosaurs. They were not whales. They were older, quieter, and built from the same simple stuff that built you and me. Begin with the water itself. The Permian Ocean was made of the same molecules that fill our oceans now. 2 hydrogen atoms bound to one of oxygen. Most of that hydrogen came from the very early universe, formed in the first few minutes after time began. Most of that oxygen was forged inside the cores of stars that lived and died long before our sun was born. When those stars collapsed, they scattered their elements into the dark. Some of that material drifted, gathered, and became Earth. So the Permian Sea, like ours, was starlight in liquid form. Into that water, life had woven shells, calcium carbonate, the same mineral that makes chalk and limestone, made the armor of countless small animals. There were brachiopods, little hinged creatures that looked like clams but were not clams at all. They sat on the seafloor in vast gardens, filtering tiny scraps of food from the current. They were so common that whole layers of Permian rock are made almost entirely of their shells. Crinoids waved in those same waters. We sometimes call them sea lilies, though they were animals, not plants. They stood on long stalks of stacked calcium discs, with feathery arms that opened like a flower at the top. When they died, their stalks broke into little buttons that still wash up in old quarries today. Hold one in your hand, and you are holding a small piece of a Permian afternoon. Around them drifted the ammonoids, distant cousins of the modern octopus and squid. They lived inside coiled shells the size of dinner plates, sometimes larger. Their bodies were soft and curious, with tentacles trailing in the water. They steered by squirting jets of seawater. Some researchers think they were intelligent, in the way modern cephalopods are intelligent. We cannot know for certain. Their minds, if minds is the right word, left no fossils. The reefs they swam past were not built by the corals we know. The reef builders of the late Permian were different animals, including sponges and strange tube-shaped creatures, all stitched together by sheets of microbes. These reefs grew slowly, in warm, shallow water, anchored to the seafloor by minerals pulled from the surrounding sea. Calcium, magnesium, silica, each atom of each mineral, had its own long history. The calcium was made in stars, the magnesium too. The silica, which is the same compound as common sand and quartz, had cycled through the planet's crust for billions of years before settling into a sponge's skeleton. The water carried other things as well: dissolved oxygen, breathed out by tiny photosynthetic life; dissolved carbon dioxide, breathed in by that same life; salt, mostly sodium and chlorine, washed down from the continents by ancient rivers; iron, in small amounts, scattered through the deep water. The iron is worth pausing on. Almost every iron atom in the Permian Ocean, and almost every iron atom in your own blood right now, was forged in the dying heart of a massive star. When such a star runs out of fuel, it collapses and explodes, and in those final moments it builds iron and flings it across space. Earth gathered that iron when it formed. Life found ways to use it. The ammonoid, steering through a Permian reef, carried the same star-born iron in its body that the modern fish does, that you do. Some of Earth's water itself may have arrived later, on icy comets and asteroids that struck the young planet. The question is not fully settled. Some scientists think most of the water was always here, baked into the rocks of the early Earth and slowly released. Others think comets delivered a meaningful share. The truth may be a quiet mixture of both. Either way, the seas the brachiopods sat in were partly a gift from the outer dark. All of this, the shells, the water, the dissolved gases, the slow-growing reefs, the drifting ammonoids, was built from a small handful of simple ingredients: hydrogen, oxygen, carbon, calcium, a scattering of metals, the same ingredients we are made of, the same ingredients that, in the next few sections, would be shaken and stirred and poisoned almost beyond recognition. The Permian Sea was not a separate world. It was our world in an earlier draft, and it was about to be edited very harshly indeed. Before the world nearly ended, it was green. Not green the way our world is green today, with grasses and flowers and broadleaf trees, but green in a stranger, older way. A single great continent stretched across the planet, a vast body of land we now call Pangea. Its name means all earth, and that is almost what it was: one enormous landmass surrounded by a single enormous ocean. Across this strange supercontinent grew forests unlike any that exist now. They were quiet forests, with no bird song, no rustle of mammals in the underbrush. The wind moved through them. Insects droned in the warm air, but the trees themselves were the main sound, creaking softly in the breeze, dropping spores instead of seeds onto the damp ground. One of the most common trees was called Glossopteris. It grew tall and straight, with long tongue-shaped leaves that turned gold in the cooler months. Glossopteris forests stretched across what is now Antarctica, India, Africa, and Australia. We know this because fossils of the same leaves appear on all these continents, even though they are now separated by oceans. Those scattered leaves were one of the first clues that the continents had once been joined. The forces shaping these forests were slow and patient. Gravity pulled rain from heavy clouds down onto the canopy. Heat from the sun fed the leaves. Pressure deep in the earth pushed the great plates of crust together, lifting mountain ranges along the seams where the old continents had merged. Those mountains caught the rain on one side and cast long, dry shadows on the other. Whole inland regions became deserts, baked under a steady sun, while the coasts stayed damp and lush. The interior of Pangea may have been one of the harshest places life had ever tried to live. With so much land in one piece, the center sat far from any ocean. No sea breeze could reach it. Summers there may have grown brutally hot. Winters may have turned bitterly cold. Geologists, studying the red rocks of that time, see the marks of dry riverbeds and ancient dunes. Some researchers wonder if these inland deserts were already stressing life long before the Great Extinction began. Others think the climate, while harsh, was steady enough that life had adapted comfortably. The question is still open. Closer to the coasts, the forests held on. In the swampy lowlands, fallen trees sank into still water and slowly turned into peat. Over millions of years, pressure and heat would press that peat into coal. Much of the coal we burn today was laid down long before the Permian, but the late Permian forests added their own slow layers. Then, at a certain point in the rock record, those layers stop. The coal simply ends. For millions of years after, almost no coal forms anywhere on Earth. Geologists call this the coal gap. It is one of the strangest features of the whole story, and we will sit with it more later. Magnetic forces were at work too, quietly beneath everyone's feet. The Earth's core churned, generating a magnetic field that shielded the surface from the worst of the solar wind. That shield held steady through the Permian, as far as we can tell. So the trouble that was coming did not come from above. It came from below, and from within the planet itself. The slow grind of plate movement was already setting the stage. Deep beneath Siberia, heat was gathering in the mantle, that thick layer of hot rock between the crust and the core. Pressure built. Magma pooled. None of this was visible from the surface yet. A Glossopteris tree, dropping its tongue-shaped leaves onto the forest floor, had no way of knowing that the ground far below was beginning to stir. What is striking, when you look at the Permian world this way, is how ordinary it seems. The forces shaping it were the same forces shaping our world now. Gravity, heat, pressure, the slow drift of continents, the patient turning of seasons. There was nothing obviously doomed about it. The forests grew, the rivers ran, strange reptiles browsed in the shade, insects hummed. And yet, somewhere in the balance of all those forces, something was about to tip. Researchers still debate which force tipped first. Was it the heat building below Siberia? Was it a slow change in ocean currents that had already begun? Was it some quiet shift in the atmosphere that we have not yet learned to read in the rocks? The forests of Pangea kept growing, dropping their leaves, drinking the rain. They did not know. We are still trying to know, looking back across 250 million years of stone. Now, we come to the part of the story where the Earth itself seems to take a long, slow breath, and then begin to release something vast from deep inside. To picture what happened in what is now Siberia, around 252 million years ago, we have to stretch our minds in ways that feel almost impossible. The numbers are so large, they start to lose meaning. So let us try to bring them down to something the body can feel. Imagine a single sheet of basalt, that dark, heavy volcanic rock, spreading out across the land. Now imagine that sheet is not the size of a town or a country, but roughly the size of the continental United States. That is the area scientists believe the The lava flows of the Siberian traps once covered layer upon layer, flow upon flow, stacked into a pile of stone thicker, in places, than the tallest mountains in the eastern half of North America. If you could lift the whole thing and set it on a kitchen table, the house, and most of the neighborhood would simply vanish beneath it. The total volume of erupted material is hard to grasp. Estimates suggest somewhere around 3 to 4 million cubic kilometers of lava, ash, and intruded rock. To shrink that down, picture a single grain of rice. Now picture enough grains of rice to fill every bathtub in every home in a city the size of Tokyo, 10 times over. Even that comparison falls short. The Siberian traps poured out enough molten material to bury the entire surface of the lower 48 states under a layer of stone, roughly half a kilometer deep. Half a kilometer. That is taller than almost any building humans have ever built. What makes this so unusual is that it did not happen in a single afternoon, or even a single century. The eruptions seem to have unfolded across hundreds of thousands of years, possibly as long as 1 million. That sounds slow, and in human terms it is unimaginably slow, but in the long, patient pace of geology, it is a sudden cough, a single, drawn-out exhalation of the planet. To feel the pace, imagine a candle that burns for your entire life, from your first breath to your last. The Siberian traps were a candle that burned for 10,000 lifetimes, steadily, without ever quite going out. The temperature of the lava itself would have been somewhere around 1100 degrees Celsius at the vents. That is hot enough to melt copper, hot enough to make iron glow soft and orange. But the heat was only part of the story. The truly strange part may have been what the eruptions did to the rocks they passed through. As the magma rose, it pushed through thick layers of coal, salt, and limestone buried in the Siberian crust. Those rocks were rich in carbon and sulfur. The heat baked them, cooked them, released their gases into the air. Here is where the scale becomes almost dizzying. Some researchers estimate that the eruptions may have released tens of thousands of gigatons of carbon dioxide into the atmosphere over their lifetime. 1 gigaton is 1 billion tons. To imagine a single gigaton, picture every car currently on Earth, all 1.5 billion of them stacked together. That is roughly 1 gigaton. Now multiply that by tens of thousands. The exact number is debated, and that is part of the open question. But no one who studies these rocks thinks the figure was small. There is still real disagreement about which gases mattered most. Some scientists believe carbon dioxide was the main driver of the long, slow warming that followed. Others wonder whether sulfur dioxide caused brief, sharp episodes of cooling between warmer pulses. A third view suggests methane, released from the heated coal beds, may have played a larger role than the lava itself. The evidence supports pieces of all three ideas. None of them, on its own, fully explains the record in the stone. What seems clear is that the eruptions were not a single event, but a long, uneven sequence. Quiet centuries, loud centuries, dome collapses, fresh fissures opening kilometers away. A landscape of black rock and pale gas, slowly enlarging across a region we now call Siberia, which back then sat at a different latitude on a different shaped world. It is humbling to sit with the size of it. A wound in the earth, larger than most modern nations, breathing out for longer than our entire species has existed. And still, the question remains unresolved. Was this enormous outpouring truly enough, by itself, to nearly end all life, or did it need help from somewhere else? Imagine drifting above the Permian Ocean as the long crisis begins to take hold. From this calm height, the water still looks the way oceans have always looked, wide, blue, endless. The surface catches the soft yellow light of a low sun. Long swells move in slow lines toward shores that no human will ever see. Yet something is changing in the chemistry just beneath that gentle blue skin. Something quiet and patient and unkind. Drop a little lower, just above the waves. The color is not quite the blue you remember from a tropical sea. It carries a faint greenish tint in places, as if the water has been steeped with something. Near the coasts, long ribbons of milky white drift along the surface. These pale streaks are not foam, and they are not clouds of fish. They may be blooms of strange microbes thriving in water that has lost its old balance. One theory holds that as carbon dioxide poured from the Siberian eruptions, the seas grew warmer and more acidic. Another idea suggests that vast plumes of sulfur shifted ocean chemistry in ways we are still working out. The evidence supports pieces of both, and the full picture remains open. Float a bit closer to the shore. The reefs that once shimmered here are no longer the bright living gardens of earlier ages. The corals of the Permian were not the same as the corals we know today. They built tall, fluted shapes, like stacks of stone cups in warm, shallow water. Now, many of those cups are pale. Their soft tissues are thinning. Some have already dissolved at the edges, leaving ghostly white outlines against the sand. When seawater grows more acidic, it becomes harder for creatures to build shells and skeletons out of calcium carbonate. This is one of the clearest fingerprints geologists read in the rock. The shelled creatures of this time leave behind layers that grow thinner, smaller, stranger, as if something in the water has begun to eat away at their armor from the moment they form. Look out across the open sea again. The horizon shimmers in the heat. The Permian world is warming, slowly and then more quickly, and the surface waters are warming first. Warm water holds less dissolved oxygen than cool water, so even before the deeper anoxia takes hold, the upper layers grow strangely thin in breathable gas. Fish that once cruised in great schools now keep closer to the cooler currents. Some species drift toward the poles, chasing temperatures that feel like home. Whether they find refuge there or only delay the loss is one of the questions still under study. Near the coastlines, river mouths spread brown fans of mud and silt into the sea. The forests inland are beginning to falter, and without deep roots holding the soil, more sediment washes down to the shore. Some researchers wonder whether this flood of nutrients fed enormous algal blooms, which then died and rotted, pulling even more oxygen from the water. Others think the algae story is only part of a larger chemical shift. The rocks preserve hints of both. They do not yet tell us which mattered most. If you could lower a hand into the water, you might notice something else. The sea feels warmer than it should at these latitudes. In some places, scientists estimate that surface temperatures climbed into ranges that would feel like a hot bath. Creatures built for cool, steady seas had no way to escape such heat. Their muscles failed. Their eggs would not develop. Their food sources thinned. The warming did not need to be sudden to be deadly. A few degrees, held for long enough, was a slow and patient killer. Look down once more. Through the gentle swells in the shallow lagoons, you can see the soft outlines of brachiopods, those small hinged shells that once carpeted the Permian seafloor. They sit half buried in the sand, their valves slightly open, as if listening. Many of them will not survive what is coming. Their lineages, once vast, will dwindle to a handful of survivors in the millions of years ahead. Whether they were lost mostly to acid, to heat, to oxygen loss, or to some combined pressure that no single cause can explain, remains an open question. From above, the ocean still looks beautiful, The blue is still wide, the light still glitters. That is part of what makes this chapter of Earth's history so haunting to think about. The surface gave little warning, the change was patient. The sourness, the warmth, the thinning breath of the water, all gathered slowly under a sky that still looked, for a long while, almost ordinary. Let us go down now, beneath the surface of those ancient Permian seas, into water that grew darker and stranger as the crisis deepened. The sunlit top of the ocean is one story, but the deep water, far below the waves, may hold the heart of the mystery. Many researchers believe the deep ocean lost most of its oxygen during the extinction. Why this happened, and how quickly, remains an open question. Oxygen in the sea comes mostly from two places. Some drifts down from the air at the surface, mixing in as wind stirs the waves. The rest comes from tiny floating plants that release oxygen as they grow. From the surface, this oxygen slowly travels downward, carried by cold, sinking currents. In a healthy ocean, even the deep water gets a steady, quiet supply. In the late Permian, something seems to have broken that gentle flow. Rocks from this time are dark, almost black, and rich in a mineral called pyrite. Pyrite forms in water that has no oxygen at all. Geologists find these black layers across many parts of the world, from what is now China to what is now Italy. The pattern suggests that vast stretches of the deep sea went still and dead, holding no oxygen for life to breathe. One leading idea is that the volcanic warming from the Siberian traps slowed the great ocean currents. Cold water sinks because it is heavy. Warm water floats because it is light. As the climate heated, the cold polar water that once dove into the depths grew warmer and less eager to sink. With less sinking, the deep ocean stopped getting fresh oxygen from above. Slowly, layer by layer, the dark water grew stale. Another idea works alongside this one. As the planet warmed, the surface water held less oxygen to begin with. Warm water simply cannot carry as much dissolved gas as cold water. You can see this in a glass of soda left out on a counter. The bubbles drift away as it warms. The same thing may have happened across the world's oceans on a far greater scale, over thousands of years. A third possibility points to the tiny life forms in the sea. When rivers carry extra nutrients into the ocean, certain microbes bloom in huge numbers. As they die and sink, other microbes break them down, and that breakdown uses up oxygen. Some researchers think the Permian rivers, swollen with eroded soil from dying forests, fed the seas too much. The microbes feasted. The deep water suffocated. These three ideas are not enemies. They may all be true at once, each one feeding the next, but the order of events and how much each one mattered is still debated. Some scientists argue the slowdown of currents came first. Others believe the warming surface was the main driver. Still others think the runoff from the land tipped a balance that was already wobbling. There is a stranger possibility too. In deep oxygen-free water, certain bacteria thrive. They breathe sulfur instead of oxygen, and they release hydrogen sulfide, the gas that smells like rotten eggs. Some researchers wonder if these bacteria spread upward through the water column during the extinction, poisoning the shallow seas as well. Chemical traces of their pigments have been found in rocks from this time. Whether they were a major killer or just a side effect of a sick ocean is still being studied. Picture, for a moment, what that deep water might have looked like. A still, lightless layer, heavy with stale gases. No fish moved through it. No worms crawled on the muddy bottom. Only mats of bacteria, slowly working in the dark, laying down those black layers of pyrite that geologists now pull from cliffs and quarries. The bottom of the ocean had become a kind of vast, silent basement, sealed off from the breathing world above. The strangest part is how long this state may have lasted. The black layers in the rock are not thin. In some places they stretch upward through many meters of stone, suggesting the deep ocean stayed oxygen poor for hundreds of thousands of years, perhaps longer. Recovery, if it can be called that, came in slow, uneven pulses. Oxygen would return for a while, then it would fade again. The sea seemed to forget how to breathe. What triggered the first loss, and what kept it going for so long, may never be fully known. The rocks remember the result, but not every step that led there. The question of the missing oxygen sits quietly at the center of the larger mystery, waiting in the dark layers of stone. And the deep water, in its long stillness, holds an answer that researchers are still learning how to read. Above the dying world of the late Permian, the sky itself may have changed. Not all at once, not in a single afternoon, but slowly, through long pulses of volcanic breath and chemical drift, the color of the air may have shifted. The blue we know so well, the soft pale blue of a clear morning, may have turned in places to something stranger, a bruised yellow, a hazy orange, a sickly green near the horizon. We cannot prove this with certainty, but the chemistry of that age makes it a real possibility, and the rocks hint at sky-changing forces, moving in long, slow rhythms. Everything in the Permian crisis seems to have moved in cycles. The Siberian traps did not erupt in one burst and then fall silent. They breathed, they pulsed. Lava flowed for centuries, then quieted, then flowed again. Across roughly 2 million years, the eruptions came in waves, each wave releasing fresh gases into an atmosphere already burdened by the last. Picture a giant slow heartbeat hidden beneath the crust, sending up pulses of sulfur and carbon and ash with each beat. Sulfur is the key to the changing sky. When volcanoes throw sulfur dioxide high into the air, it forms tiny droplets called aerosols. These droplets scatter sunlight. They cool the surface. They tint the heavens. Some researchers wonder whether long stretches of the late Permian skies looked milky and pale, the sun a small bright coin behind a soft veil. Other thinkers argue the opposite, suggesting the sulfur load was uneven and patchy, leaving wide regions under skies that still looked mostly normal, with strange colored bands only near the eruption zones. After each pulse of sulfur cooling, the carbon dioxide would linger. Sulfur aerosols wash out in years. Carbon stays for many thousands, so the rhythm of the crisis may have looked something like this: a pulse of eruption, a brief cool spell, grey and dim, then a longer warming, hotter than before, as the carbon piled on, then another pulse, another short cool, then deeper heat. Each cycle pushed the climate further from where it had been. Each cycle stripped away a little more of the old world. The oceans pulsed too. Warmer seas hold less oxygen, so the cycles of heat may have driven cycles of suffocation. When the air cooled briefly under sulfur haze, the seas may have caught their breath, oxygen creeping back into shallow waters. When the heat returned, the breath was lost again. Some scientists think this is why the marine extinction came in pulses rather than one clean stroke. Life almost recovered, then almost recovered again, each near recovery cut short by the next swing of the slow planetary pendulum. The land breathed in its own rhythm. Forests would have died back during the worst spells, then tried to return during the brief recoveries, only to fall again. Pollen counts in the rock record show this stutter. In some places, layers of dead wood and ash alternate with thin signs of returning green. Then more ash, then more green, like a heart that keeps trying to start. The forests of Pangea were not erased in a single afternoon. They were exhausted across thousands of years of trying and failing. Even the chemistry of rainfall may have followed a pulse. Sulfur in the high air mixed with water vapor and fell as acid rain, dissolving leaves, scorching soil, leaching minerals from stone. During the worst pulses, the rain itself may have stung. Between the pulses, it softened. Then the next pulse came. The exact strength of this acid rain remains debated. Some studies suggest brief, severe episodes near the eruptions. Others suggest a milder, more widespread effect spread across continents. Through all of this, the sky kept its quiet rhythm of day and night, of moon and tide, of season and orbit. The planet itself never stopped turning. Earth did not pause. The stars still wheeled overhead, the same stars our ancestors would one day name. From orbit, if anyone had been watching, the changes might have looked subtle, almost graceful. A slow tinting of the atmosphere, a creeping pale across the seas, a dulling of the green on the great supercontinent. Nothing sudden, nothing dramatic to a distant eye, only a long, soft, fading breath by breath, pulse by pulse. What we cannot say is which pulse mattered most. Was there a single eruption cycle that pushed the world past a hidden threshold? Or did the cumulative weight of many smaller cycles finally crush thee? Before the Great Dying, the warm, shallow seas of the Permian world were ringed with reefs. These were not quite like the coral reefs of today. The builders were different, sponges with stony skeletons, calcified algae, and small colonial animals called bryozoans worked together over thousands of years to raise long ridges of limestone beneath the sunlit water. Tabulate corals and rugose corals, two ancient groups now long vanished, added their own patient layers. The reefs grew slowly, the way old stone walls grow in a meadow, one quiet century at a time. These reef systems were among the richest neighborhoods on the planet. They sheltered brachiopods, clinging to crevices, crinoids waving like underwater flowers, small fish gliding through the shadows, and trilobites in their final chapters of existence. Around the reefs, the open shelf seas held ammonoids with their coiled shells drifting slowly through the blue. Beyond the shelves, the deep ocean stretched on, dark and still. The reefs were the bright edges where life pressed itself against the light. Then, in the rock record, the reefs simply stop. Geologists call this break the reef gap. For a stretch of time that may have lasted somewhere between 8 and 10 million years, no large reef structures appear in the stone anywhere on Earth. Not in the rocks of what is now China, not in the rocks of the Alps, not in the rocks of the American West. The reef builders that had shaped the Permian seas, the tabulate corals, the rugose corals, the calcified sponges of that particular kind, are gone. Many never return. The ocean, in a sense, forgets how to build. This long silence is one of the strangest neighbors to the extinction itself. The death of so many species is one mystery. The slow refusal of the seas to rebuild the reef ecosystem is another. And researchers are still uncertain why the gap lasted as long as it did. One idea is that the chemistry of the oceans simply would not allow reefs to grow back quickly. If the seas became more acidic, as some evidence of carbonate dissolution suggests, then the tiny animals that pull calcium carbonate from seawater to build their skeletons would have struggled. A coral or a sponge trying to lay down its stony frame in sour water is like a mason trying to build a wall while the bricks dissolve in his hands. Under this view, The chemistry needed millions of years to settle before reef builders could thrive again. A competing viewpoint instead to the loss of the builders themselves. Reefs are not just chemistry, they are partnerships. They depend on specific animals, specific algae, specific microbes living closely together. When the Permian reef builders died out, the partnerships died with them. Even if the water grew gentle again, there may have been no one left who knew the old craft. Under this view, the gap is less about poisoned seas and more about missing tenants. The new reef builders of the later Triassic, the ancestors of modern stony corals, had to evolve almost from scratch, and that takes time. A third possibility blends the two. Perhaps the chemistry stayed harsh in pulses, killing off each early attempt at recovery before it could take hold. Microbial mats, those slimy living crusts that once dominated the early Earth, briefly came back during this interval. In the early Triassic, strange flat reefs made entirely of microbes appear in the rock as if the ocean had slipped backward by 2 billion years. Why did the microbes return so strongly? No one is quite sure. They may have filled the empty space left by the missing animals. They may have thrived because predators that normally grazed them were gone. The question is open. What seems clear is that the neighbors of the dying reefs felt the loss for a very long time. Fish lineages that had specialized in reef life dwindled. Brachiopods that had clung to reef walls became rare. The crinoids that survived were different from the crinoids that had come before. The shape of the shallow sea changed, and with it, the shape of every life that depended on those bright edges. Reefs today face their own pressures, and scientists sometimes look back at the Permian Gap with quiet attention. The deep past does not predict the present, and the differences are large. But the long silence in the stone is a reminder that an ecosystem can vanish faster than it can return. The reefs of the Permian took perhaps 200 million years to build their final form. They disappeared in a geological breath, and the sea did not rush to replace them. In the rocks that mark the end of the Permian, geologists noticed something strange. A thin, dark band running through cliffs in many parts of the world. When they looked at it closely under a microscope, they saw what appeared to be tiny threads. Threads woven through the stone like the roots of something soft and forgotten. Some researchers believed they were looking at the remains of fungi, an enormous bloom of fungi that may have spread across the whole dying world. This layer became known to scientists as the fungal spike, and it sits at one of the most extreme moments in the entire fossil record. The thought is gentle, but staggering. After the great forests fell, after the seas turned sour, after the air filled with ash and acid, the land may have belonged for a time to mushrooms, to molds, to the quiet decomposers that feed on death. Picture it slowly, the way one drifts into a dream. A landscape of fallen trees, trunks lying broken across pale, cracked soil. No green leaves moving in the wind, because there is no wind to speak of. Only a still, heavy haze, and across this silent ground, soft, pale growths spreading. Threads creeping over bark, caps pushing up through layers of dust. A world hushed under a slow tide of decay. The extreme part is the scale. Fungi normally play a quiet role in any forest, breaking down what has fallen so that new life can grow. They live mostly out of sight, hidden in the soil. But in this layer of rock, the threads appear in such great numbers across so many continents that some researchers believe the whole planet became, for a moment, a single vast decomposer ecosystem. A world where the main work being done was the slow undoing of what had lived. One theory says the fungi feasted on the dead forests, With so many trees killed, all at once, so much wood lying down, the fungi had more food than they could ever normally find. They bloomed in numbers no earth had seen before or since. And then, as the wood was used up, they faded back to their quiet background role. A competing view is more cautious. Some scientists who looked again at those tiny threads in the rock argued that they may not be fungi at all. They might be the remains of algae, or the broken cells of tough land plants that survived in patches. Under the microscope, ancient threads can be hard to tell apart. The fungal spike, in this view, may be a fungal and algal spike, or even mostly algae mistaken for fungi. The truth probably lies somewhere in between, and the debate is still open. Either way, the extremity of that thin, dark layer is hard to escape. It marks a time when complex plants struggled, when tall trees became rare, when the simple, the small, and the patient seemed to do better than the grand and the leafy. Life had not ended, but life had been turned for a while, almost inside out. Other extremes pile up at this boundary. Tropical sea surface temperatures, reconstructed from the chemistry of fossil teeth, may have climbed to around 40 degrees Celsius in shallow waters. That is hotter than a warm bath. Fish that need cooler water seem to vanish from equatorial rocks entirely. Some researchers describe a wide band around the ancient equator as a dead zone, for many animals too hot to live in for long. The land may have grown stranger still. With forests gone, soils began to wash away. Rivers carried enormous amounts of mud and grit into the sea. In some places, the rock record shows a sudden flood of red sediment, as if the bare ground itself were bleeding into the oceans. Whether this lasted for thousands of years or for hundreds of thousands is another question that remains open. And under it all, the fungi, or whatever those threads truly were, kept doing their slow work, breaking down, returning, closing the long account books of the Permian world. It is a strange image to hold in the mind as sleep approaches. A planet whose loudest living voice, for a brief geological moment, may have been the soft hush of decay. No roar of great beasts, no rustle of vast canopies, only the patient spread of pale threads through fallen wood, under a sky still thick with the breath of distant volcanoes. Whether that picture is exactly right, we cannot say with certainty. The rocks hint, the microscopes suggest. The debate continues among careful, curious people who have spent their lives reading these dark, thin layers. For now, the fungal spike sits in the record as one of the most extreme and most quietly haunting clues to what the dying world became. If you wandered through the world just after the Great Dying, you might first notice something strange about the rivers. They had forgotten how to wind in the rocks left behind from the early Triassic. Geologists find a quiet little puzzle. The patterns of ancient riverbeds change. Before the extinction, many rivers wandered across the land in long, slow curves, the way most large rivers do today. After the extinction, those curving channels almost vanish from the record. In their place, braided rivers spread out, shallow and tangled, like loose threads of water running across bare ground. This shift is small. You could walk past these stones 100 times and never notice. But to a geologist who reads the soft layers of mudstone and sandstone, it whispers something tender about a wounded world. Curving rivers need plants, they need roots, holding the banks together, gripping the soil so the water carves a single, patient path. When the roots are gone, the banks crumble. The river spreads thin. It splits and rejoins and splits again. It forgets the slow art of meandering. One quiet theory is that the loss of land plants after the Permian crash was so complete that for a time The very shape of rivers across the supercontinent changed. Some researchers see this as strong evidence that vegetation truly collapsed worldwide. Others wonder if the picture is more local, recorded clearly in some basins and barely at all in others. The question of how universal this river change really was remains open, debated over coffee in quiet university hallways. There are other small details that scientists find beautiful. Inside the boundary rocks, in places like southern China and the Italian Alps, you can sometimes find tiny grains called framboids. The name comes from the French word for raspberry, because under a microscope, they look like miniature clusters of perfectly round beads. They are made of iron and sulfur, and they form in water with very little oxygen. The size of these framboids matters. Where they are small and uniform, it suggests the seawater was almost completely starved of oxygen, even near the surface. Their tiny shapes are one of the gentlest fingerprints left by an ocean that may have been quietly suffocating. Then there are the spores. In rock layers from the boundary, palynologists, scientists who study ancient pollen and spores, sometimes find an odd abundance of misshapen, malformed spores. They are puckered, twisted, sometimes split open. One idea is that this points to a stressed atmosphere, perhaps high in ultraviolet radiation, perhaps poisoned with metals. Another idea is that the malformations come from heat shock or from soils gone sour with acid rain. The little spores cannot tell us which. They only carry the marks of having grown up in a difficult world. In some marine layers, geologists find thin films of pyrite, the mineral often called fool's gold. They glint faintly when broken open, soft yellow against dark mudstone. In a healthy ocean, pyrite forms only in oxygen-poor pockets deep in the mud. After the extinction, pyrite spreads upward into rocks that should have formed in shallow, sunlit water. It is a small mineral, but it tells a quiet story of seas where the dead zone climbed toward the surface. There are odd carbon shifts too, recorded in the chemistry of limestone. The ratio of carbon atoms changes sharply across the boundary, jumping back and forth in pulses. Each pulse is invisible to the eye. You would need a mass spectrometer to see them, but each one likely marks a great breath of carbon released into the air, perhaps from the Siberian eruptions, perhaps from methane bubbling out of the warming oceans. Researchers still argue about exactly what each pulse means and how many separate events the carbon record holds. Tiny conodont teeth, no bigger than a grain of rice, also help mark the boundary. Conodonts were small, eel-like creatures, and their hard, tooth-like fossils change in subtle ways across the extinction. Their shapes, their chemistry, even the oxygen isotopes locked inside them, help scientists reconstruct ancient sea temperatures. Those readings suggest tropical oceans may have grown hot enough to be hostile to most life. The little teeth are quiet messengers from a fevered sea. These are the details that thrill the scientists who study them. The braided rivers, the raspberry crystals, the wrinkled spores, the thin yellow shimmer of pyrite. Each one is a small note in a long, soft song about a world that nearly emptied itself. None of them alone solves the mystery. Together they sketch the outline of something vast and still incomplete, a shape we can sense more than. The idea that the seas themselves had rotted is a strange one, and it took a long time to arrive. For most of the history of geology, the great extinction at the end of the Permian was seen, when it was seen at all, as a kind of quiet gap in the rocks. The old fossils ended, the new fossils began. Between them lay a thin, troubled layer that few people thought to question. The story of how that layer came to be red as a poisoned ocean is itself a slow tale. built up over more than a century by patient hands. In the late 1800s, a Scottish geologist named Roderick Murchison gave the Permian its name. He took the word from the old Russian region of Perm, where he had walked across pale limestones full of strange shells. He saw that something ended there. He could not yet say what. The tools of his time were a hammer, a notebook, and a careful eye. He sorted fossils by hand and matched them across long distances. He noticed that above a certain layer, whole families of creatures simply disappeared. He had found the edge of the extinction without knowing its scale. For decades after, the cause remained quietly unspoken. Some early thinkers blamed slow climate change. Some blamed the joining of the continents into Pangea, which would have drained shallow seas and pushed coastal life into smaller and smaller pockets. These were reasonable ideas, and parts of them may still be true, but they did not explain the silence in the deep ocean rocks, where life had also failed. They did not explain why even creatures far from any shoreline had vanished. The real shift came in the late 20th century, when geochemists began to read the chemistry of old rock in finer and finer detail. They learned to measure the balance of certain elements, like sulfur and carbon and uranium, locked inside ancient mudstones. Each element carries a quiet signature. Each signature can hint at the conditions of the water that once lay above. When researchers turned these tools on the boundary layer, the patterns surprised them. The carbon balance lurched, the sulfur balance lurched with it, and in many cores, drawn up from old seabeds, there appeared the chemical fingerprint of water that had lost almost all of its oxygen. In some places, there were even traces of hydrogen sulfide, the foul gas that smells of rotten eggs. This gas is made by certain bacteria that thrive only when oxygen is gone. Their presence, written in the rock, suggested that vast stretches of the Permian Ocean had stagnated. The water had gone still, the deep layers had soured, the bacteria had multiplied, and the gas they made may have risen into the shallows, where it would have been deadly to nearly every breathing thing it touched. This is the theory of the rotting seas. Some researchers call it the euxinic hypothesis, from an old Greek word for the Black Sea, whose deeper waters are themselves still oxygen-starved today. The idea is that the late Permian oceans, warmed by volcanic gases and weakened in their normal mixing, slipped into a kind of slow chemical illness. The illness spread upward, the illness spread outward, and it lingered long enough to break the chains of ocean life from below. It is a striking picture, and the evidence for parts of it is genuinely strong. Yet not everyone agrees on how much of the extinction it explains. Some scientists believe the rotten waters were the main killer. Others believe they were only one symptom of a larger collapse, alongside heat, acid, and a poisoned atmosphere. A few wonder whether the hydrogen sulfide ever truly reached the surface at a global scale, or whether it stayed mostly trapped in certain basins. The signatures appear clearly in some cores and faintly in others. The story is not the same in every ocean. So the theory of the rotting seas is less a final answer and a slowly built case, assembled by chemists and geologists working in quiet labs across many decades. Each new core drilled from a remote outcrop adds another small piece. Each piece sharpens the picture and softens it at the same time. We can now say, with reasonable confidence, that something went very wrong with the chemistry of the late Permian Ocean. We cannot yet say exactly how widespread the sourness became, or how much of the dying it directly caused. The discovery is still unfolding. The hammers have given way to mass spectrometers, but the patient watching of the rock continues. Somewhere in a drawer of dark mudstone, the next clue is already waiting. Most of us, when we think of a mass extinction, think first of an asteroid. We picture a great rock falling from the sky, a flash of light, and the long winter that follows. That image belongs to a different extinction, the one that ended the age of the dinosaurs many millions of years later. For the Permian event, the story has always been told in slower tones: volcanoes, sour seas, a world poisoned from within. And yet, quietly, for decades now, a small group of researchers has been listening for something else. They have been listening for the whisper of a distant impact at the close of the Permian too. The idea sounds strange at first. The rock layers from the end of the Permian do not show the clean signature that the later impact left behind. There is no thick global blanket of shocked dust. There is no bright band of iridium, that rare metal, more common in space rocks than in Earth's crust, lining the boundary in every quarry on every continent. The fingerprint that made the later impact so easy to read is simply not there in the same bold way. For most geologists, that absence has been answer enough. No clear fingerprint, no impact, but the story has a few odd footnotes in rocks from this boundary. In places as far apart as Antarctica and southern China, researchers have found tiny grains of strange material. Some of these grains are buckyballs, round cages of carbon atoms, and inside a few of them, trapped like notes in a sealed bottle, are gases with a chemistry that some scientists believe matches space, not Earth. Other grains show patterns of fracture that look, under the microscope, like the shock marks left by something striking the ground at unimaginable speed. None of this is conclusive. Each finding has been questioned, re-examined, defended, and questioned again. Then there is the curious case of a possible crater. Off the northwestern coast of Australia, beneath the seafloor sediments, lies a vast circular structure called Badut. Some researchers have argued that Badut is the buried scar of a giant impact that struck near the end of the Permian. They point to features in the rock there that to their eyes resemble the shattered cores of other known craters. Other researchers look at the same data and see something quite different. To them, Badut is a volcanic feature, or a quirk of the deep crust, not a wound from the sky. The debate has gone back and forth for years, with neither side fully convincing the other. There is also a strange structure beneath the ice of East Antarctica, in a region called Wilkesland. Gravity readings there show a great circular dimple in the rock far below the glaciers. A few scientists have wondered whether this might be the buried ghost of an enormous impact crater, possibly old enough to match the Permian boundary. Others suspect it is simply a feature of the deep continental basement, shaped by forces that have nothing to do with anything falling from above. Because the ice sheet covers it completely, no one has yet been able to walk across the rock and test the question directly. It remains, for now, a shape in the gravity data, and little more. What makes all of this so quietly fascinating is the gap between expectation and evidence. If a great impact truly struck Earth at the close of the Permian, you would expect its fingerprint to be obvious, written into every continent. Instead, the clues are faint, scattered, and easy to read in more than one way. Some scientists take that faintness as proof that no impact happened at all, and that the Siberian volcanoes and the suffocating seas are story enough. Others wonder whether an impact did occur, but in a place or a way that left only the softest trace, perhaps into deep ocean crust that has since been swallowed back into the mantle, leaving little behind. The honest answer, for now, is that we do not know. The volcanic story is strong, supported by abundant evidence in rock and chemistry. The impact story is weak, supported only by whispers. But whispers are not nothing. Science has been surprised before by quiet signals that turned out to matter. So the question stays open at the edge of the field, raised now and then by a new core sample, a new mineral grain, a new circle in the gravity data, somewhere beneath the ice, or beneath the sea, or perhaps nowhere at all. There may be a scar we have not yet learned to read, and we listen gently for what it might one day say. There is a question that has followed researchers for decades, quiet but persistent. When the great dying came, did it arrive slowly, like a long winter settling over the world, or did it strike quickly, in a series of sharp blows the planet could not absorb? The rocks seem to whisper both answers at once, and that is part of what makes this mystery so deep. For a long time, many geologists pictured the extinction as a slow unraveling. The Siberian traps, those endless floods of dark basalt in the far north, did not erupt in a single night. They poured out across thousands of centuries, building lava plains thicker than mountains. In that view, the world weakened gradually. Forests thinned, reefs faded, oxygen drained from the deep sea, one slow breath at a time. The dying was a long fading of the light, not a single closing door. Other researchers, studying thin layers of stone near the boundary, came to a different feeling. In some sections of rock in southern China, the extinction appears to compress into a startlingly thin band. The fossils above and below tell two completely different stories of life on Earth, and the change between them seems to happen across just a few tens of thousands of years. In deep time, that is, the blink of an eye. To these scientists, the great dying looks less like a slow winter and more like a sudden collapse, a moment when many systems gave way at once. Both pictures may be true at the same time, and that is where the symphony begins. Volcanoes do not act alone. Their gases reach upward and outward, touching every system the planet has. Sulfur from the Siberian eruptions could have cooled the air for short stretches, dimming the sun behind a pale haze. Carbon dioxide from the same eruptions could have warmed it for far longer, lingering in the sky long after the ash settled. The land felt one rhythm, the ocean felt another, the forests felt a third. Each system answered the volcanoes in its own time. The sea and the sky are bound together more tightly than they look. Warm air holds less wind. Slower winds stir the ocean less. A less stirred ocean carries less oxygen into its depths. So, a warming sky, born from volcanic carbon, may have quietly suffocated the deep water far below. The deep water, in turn, released methane and hydrogen sulfide as it grew sour, and those gases drifted back up into the sky. One system fed the other. The harm did not travel in a straight line. It looped, and each loop pulled the world a little further down. The forests played their own part in this gentle, terrible chorus. Healthy forests pull carbon from the air and lock it into wood and soil. When the great Permian forests began to thin, the planet lost one of its steadiest helpers. Carbon that should have been buried stayed in the sky. The sky grew warmer. The seas grew warmer still. Coral reefs, which depend on cool, clear water, faltered. Without reefs, the shallow seas lost their shelter, and countless small creatures had nowhere left to hide. One quiet loss made the next loss easier. This is why the slow death and sudden death debate may not have a single winner. The slow side is real. The volcanoes erupted for ages. The carbon built up across long stretches of time. The world warmed gradually, and many species likely declined long before the final collapse. The sudden side is also real. Once enough systems weakened together, the planet may have crossed an invisible line. Past that line, small pushes caused large falls. A modest warming triggered a sudden release of seabed methane. A sudden release of methane triggered a sharper warming still. The dying slow for 1 million years finished in 100,000. Some researchers describe this as a cascade, where one falling piece knocks down the next. Others describe it as a chord, where many notes sound together until the whole becomes unbearable. Both images point at the same idea. The Earth is not a stack of separate stories. Air, water, stone, and life share one long conversation, and when that conversation tips into harm, the harm spreads through every channel at once. We still do not know exactly how the slow drift and the sudden break fit together. We do not know which thread snapped first, or whether the question of first and last even makes sense for a wound this wide. What we have are layers of rock scattered across the world, each holding a small piece of a much larger song. The full melody, the way the systems truly played against one another, remains just out of reach, waiting quietly inside the stone. In every great dying, something stays behind. A few quiet lineages always slip through the narrow door, often in ways that surprise us. The Permian crisis was the harshest test life on Earth has ever faced. And yet, when the dust thinned and the seas grew still, a small handful of creatures were still there, breathing, eating, raising the next generation in a half-empty world. The strange thing is how unevenly the survival worked. You might expect the strongest, fastest, most fearsome animals to come through. Instead, the survivors were often small, plain, and patient. They were the weeds of their world, snails, the size of a fingernail, simple clams, tough little brachiopods, burrowing reptiles, no bigger than a house cat, the grand creatures of the Permian seas, the ones with elaborate shells and bright spines, mostly vanished from the rock record. The meek, in a sense, inherited what was left. Researchers still wonder why this happened. One idea is that small, simple bodies needed less oxygen and less food. In a world where both were running short, that may have been the deciding gift. Another idea is that burrowers had a hidden advantage. They could hide in cool, damp sediment when the surface turned hot or sour. A third idea points to flexible diets. Animals that could eat almost anything had a better chance than picky specialists. The evidence supports all three in different places for different species. It does not yet point to a single rule. One creature often mentioned in this story is a small, stout reptile called Lystrosaurus after the extinction. Its bones appear in rock layers across what is now South Africa, India, Antarctica, and China. For a stretch of early Triassic time, Lystrosaurus may have been one of the most common land animals on Earth. Imagine a low, barrel-shaped body, short legs, a beaked face for cropping plants, and two small tusks. Now imagine herds of them, wandering across muddy floodplains under a pale sky, with very few predators left to chase them. It is a strange picture. A planet ruled briefly by one humble survivor. Why Lystrosaurus made it through is still debated. Some researchers believe its burrowing habits sheltered it from heat and bad air. Others suggest its lungs were unusually efficient, well suited to a low oxygen world. Still others argue it simply got lucky, finding itself in the right places at the right time. The truth may be a mixture. We cannot interview the dead. In the sea, the survivors tell a similar story of quiet strength. Certain mollusks and certain small fish carried their families forward, while the great reef builders went silent. The microbes, of course, kept doing what microbes always do. Mats of bacteria spread across shallow seafloors that had once belonged to corals. For a while, the oceans may have looked the way they had looked 1 billion years earlier, before complex life rose up. It was as if Earth had pressed a pause button and then quietly rewound a few chapters. The changes did not stop with the extinction itself. The recovery, slow and uneven, reshaped the living world over millions of years. New body plans appeared. Old roles were filled by strangers. The first true dinosaurs were still far in the future, but their ancestors were already walking among the survivors. Somewhere in those small, scaly, unremarkable bodies lay the seed of the age to come. None of them knew it. They simply lived and ate and tried not to die. What this means for the bigger question is gentle and humbling. The Permian crisis did not just kill. It also chose. It chose which traits would be carried into the next world and which would be left in the stone. We do not fully understand the rules of that choosing. Some scientists wonder if survival was mostly about biology, about lungs and blood and behavior. Others wonder if it was mostly about geography, about being in a sheltered valley or a deep, cool basin when the worst arrived. The evidence keeps pointing in both directions at once, and the slow transformation continues, in a way, even now. The descendants of those Triassic survivors are still here, scattered through modern ecosystems. Some snails in tide pools today carry shapes very close to their Permian cousins. Certain ferns, certain fungi, certain humble little forms have changed remarkably little. They are living reminders that the cracks of the world can sometimes hold more life than the great open spaces. The question of why they stayed and why their grander neighbors did not is still being asked. We have many partial answers. We do not yet have a whole one. There is a soft, low light that lives inside coal. Not a light you can see with your eyes, but a light remembered in the rock. Every dark seam of coal began as a green forest, drinking sunlight, weaving that sunlight into leaves and bark and roots. When the forest died and sank into a swamp, the buried plants kept that ancient sunlight folded inside them. Coal is, in a way, fossil light. For hundreds of millions of years, the earth pressed sunlight into stone like this. Layer after layer of green forests fell, drowned, and slowly hardened into black ribbons of carbon. Geologists can follow these ribbons through time. They appear in rocks from the Carboniferous, when giant tree ferns ruled the swamps. They appear in the Permian, when seed ferns and conifer-like trees spread across the supercontinent. And then, at the boundary where the Permian ends and the Triassic begins, the ribbons stop. For nearly 10 million years afterward, there is almost no coal in the rock record, none at all in many places. The forests that had buried sunlight for hundreds of millions of years simply stopped doing it. Geologists call this strange silence the coal gap, and nobody can fully explain it. One idea is the simplest. The forests died. The great peat-forming trees of the Permian were wiped out in the extinction, and the species that survived were not the kind that build thick swamps. Without the right plants, no peat. Without peat, no coal. The world kept growing things, but they were small, scattered, scrubby, pioneer plants, the kind that move into burned ground, the kind whose remains rot away before they can pile up into seams. In this view, the coal gap is a portrait of a forest world that had not yet been rebuilt. But there is a quieter, stranger idea woven beside that one. Some researchers wonder whether the climate itself simply refused to make coal. Coal needs not only trees, but standing water, soggy lowlands where dead plants can be buried before they decay. If the early Triassic was too hot, too dry, or too unstable, the swamps may have failed even where plants survived. The light still fell on the land. The leaves still caught it, but the water did not stay long enough to lock that light into stone. Both ideas may be true at once, and both leave gentle puzzles behind. If you stood on a Triassic riverbank in those long, quiet millions of years, the light would have looked different from any forest light we know now. There would be no canopy, no deep green shade. Imagine instead a low, open ground cover of small plants with bare red soil between them. The sky might have been hazy from lingering dust and sulfur. Sunlight would have reached the earth almost everywhere, unfiltered, harsh, hot, a world without much shadow. A world without the slow, dim, leaf-broken light that forests give. That kind of light may have shaped which animals could live and which could not. Many creatures need shade. Many small ones need leaf litter. The soft brown blanket of fallen leaves where insects, worms, and tiny lizards make their homes. Without forests, that blanket vanishes. The ground becomes a bright, exposed place. Some researchers think this open, sunlit ground is one reason recovery took so long. The web of small lives had nowhere to hide. The mystery deepens when geologists look at fossil pollen from those years. They find spores from ferns and lycopods, the same kind of plants that today colonize land after wildfires or volcanic eruptions. These are the green pioneers, the patient first arrivals. They show up again and again across the world, in layer after layer. The land kept trying, forests kept attempting to return, and something, again and again, kept knocking them back down. Was it repeated pulses of volcanic gas from the Siberian traps still smoldering far to the north? Was it acid rain stripping the soil? Was it heat waves that simply cooked seedlings before they could grow? The answers are not settled. The coal gap is one of the clearest signs that whatever happened at the end of the Permian did not end cleanly. It echoed for millions of years. When coal finally does return to the rock record, deep in the Middle Triassic, it returns shyly, thin seams, small swamps, new kinds of trees, slowly learning the old trick of folding sunlight into stone. The forests had to be reinvented almost from scratch. And the question, still resting in those dark seams, is this: what was it about the world, for those long, quiet millions of years, that would not let the light be buried? Picture, if you can, the sound of a world hollowed out. Not silence exactly, but something close to it. The wind moves across a plain of grey ash, and there is no bird song to interrupt it, because birds will not exist for another 150 million years. There are no insects humming in tall grass, because tall grass has not yet been invented. There is only the dry whisper of dust against dust, and somewhere far off, the low groan of the Siberian traps still venting their slow breath into the sky. Into this hush walks a small, hunched animal. Its body is barrel-shaped, its legs splayed slightly to the sides. It has tusks, two short ones set into a beaked face. Scientists call it Lystrosaurus. For a brief stretch of deep time, this creature was, in some places, almost the only large land animal left. Imagine the soft, padded sound of its feet pressing into the warm ash. A slow shuffle, a pause, another shuffle. That perhaps was the loudest sound on entire stretches of the early Triassic floodplain. We cannot truly know what the world sounded like in the years just after the extinction. Sound does not fossilize, but we can guess at what was missing. The great forests at once filled the air with creaking branches, and falling cones had thinned to scrubland. The reef communities that once clicked and rustled with countless small lives had gone quiet beneath stagnant water. The rivers, no longer braided through deep roots, ran wide and shallow and made a different sort of murmur than they once had. Some researchers wonder whether Lystrosaurus dominated because it was simply tough, built to breathe thin, foul air with oversized lungs. Others suspect it was lucky, a burrower whose habit of digging may have sheltered it during the worst pulses. A third view holds that its diet of low, hardy plants gave it an advantage when nothing else green remained. The honest answer is that we do not know which of these mattered most, likely some blend of all three. The fossil record gives us bones and burrows, but not motives. What is striking in the rocks of South Africa and Antarctica and China and India is how often the same small face turns up. In some beds, Lystrosaurus fossils make up the great majority of all four-legged animals found. That kind of dominance by a single species is rare in healthy ecosystems. It is the signature of a world stripped down, of a stage with most of its actors gone. Try to hear then the sound of that lonely rain, a herd of these stout animals at a muddy waterhole, the soft slap of tongues against still water, low grunts perhaps, though we cannot prove they vocalized, the shuffle of so many bodies in one place because the safe places were few. Above them, no calls of pterosaurs, because pterosaurs have not yet appeared. No screech of anything overhead at all. Only the heavy quiet of a sky still carrying a faint haze of sulfur. There are other sounds we can guess at in this aftermath world. The hiss of acidic rain falling on bare rock, where soils had washed away because the trees that anchored them were gone. The deep thrum, far underground, of basalt still cooling beneath Siberia. The slow rumble of seismic settling as the crust adjusted to the weight of new lava fields, the size of a continent. And in the seas, a different absence. Coral reefs make a soft, constant noise in healthy times. The snap of small shrimp, the grazing scrape of fish teeth on stone. After the extinction, that texture went missing for millions of years. The shallow seas would have sounded, instead, like a slow lapping over empty sediment. Microbial mats spread where coral once stood. They made no sound at all. The mystery of why Lystrosaurus, and not some other survivor, became the symbol of this hush remains open. New fossil sites in Antarctica continue to refine the picture, and some recent work suggests its dominance may have been overstated in old accounts. Perhaps the world was a little less lonely than we once imagined. Perhaps small lineages we have not yet found shared those plains, leaving fewer bones behind. Each new dig adjusts the balance. What does not adjust is the overall shape of the quiet. A planet that had hummed with countless voices for hundreds of millions of years went for a long pause, almost still. We will never hear that pause directly. We can only stand in the rock layers that record it and imagine the soft footfall of a small tusked animal crossing the ash, alone with the wind. There is a strange beauty in the way geologists measure time. They count it in layers of stone, in the slow drift of chemicals, in the patient ticking of atoms inside ancient crystals. And when they turn these tools toward the recovery from the great Permian dying, they find numbers that almost seem too large to hold in the mind. The world did not simply bounce back. It took its time. The math of that recovery is gentle and slow and full of quiet wonder. Most extinction events leave a scar in the rock that heals within a few 100,000 years. Life returns. Reefs rebuild, forests fill back in. But the Permian recovery is different. The numbers are stretched out, almost impossibly so. By many measurements, full ecological recovery took between 5 and 10 million years. Some studies push that estimate even further. For comparison, the entire history of our own species, from the earliest stone tools to this very night, fits inside roughly 3 million years. The empty world after the Permian lasted longer than that, perhaps 2 or 3 times over. Scientists arrive at these numbers in a few different ways, and the methods themselves carry a kind of quiet elegance. One approach uses tiny crystals called zircons, found in volcanic ash layers. Zircons trap small amounts of uranium when they form, and uranium decays into lead at a steady, predictable rate. By measuring the ratio of uranium to lead inside a single crystal, geologists can calculate with surprising precision the year the ash fell, not the century. The year, give or take a few thousand. From sand-sized grains, they read the calendar of deep time. Another method counts the variety of fossils through layer after layer of rock. Geologists tally how many species appear in each slice of stone, then watch how that number changes upward through time after the extinction boundary. The count drops to almost nothing. Then, layer by layer, it climbs again. The slope of that climb is the math of recovery. And in the early Triassic, the slope is gentle, painfully gentle. Diversity creeps upward in small, halting steps, as if life were testing each new idea before committing to it. There is also the carbon signal, which oscillates in strange ways for millions of years after the extinction. Carbon comes in slightly different forms, called isotopes, and living things prefer one form over another. When ecosystems are healthy and stable, the ratio of these isotopes stays calm. After the Permian boundary, the ratio swings wildly up and down for the next 5 million years. Each swing suggests another disturbance, another crisis, another stumble before the world found its balance. The math, drawn as a line on a graph, looks like a heartbeat that cannot settle. Why the recovery took so long is itself an open question, and several theories sit side by side in the literature. One idea holds that the Siberian volcanism kept erupting in pulses for hundreds of thousands of years, repeatedly poisoning the air and seas before life could gain a foothold. Another suggests that the ocean stayed low in oxygen for far longer than anyone first suspected, leaving the deep waters hostile to complex animals well into the Triassic. A third possibility points to the climate itself, which seems to have stayed unusually hot for millions of years, with equatorial seas perhaps reaching temperatures that no large marine creature could tolerate. These theories do not cancel each other out. They may all be partly true, layered together. The shapes of the survivors also tell a mathematical story. In the early Triassic, the average size of marine animals stayed small for a long time. Tiny clams, tiny snails, tiny fish. It is called the Lilliput effect, named after the land of small people in an old novel. The numbers show that body size did not return to Permian norms for several million years. Whether this was because food was scarce or oxygen was low, or because small things simply breed faster and outpaced larger competitors, no one is entirely certain. What stays with you when you sit with these numbers is the patience of the planet. 5 million years of slow climb, 10 million years of trembling carbon, 100,000 years between zircons in a single ash bed. The Earth does not rush. It measures recovery in spans that dwarf every human chronicle, every empire, every memory, and somewhere in that long, quiet stretch of the Triassic, the ancestors of nearly everything alive today were already there, small, hidden, beginning again. The math is not a calendar of loss. It is a calendar of return, written one slow grain at a time, in stone that is still patiently being read. In the Great Basin of South Africa, where the dry grass bends in the wind and the hills roll on in soft brown waves, the ground itself holds one of the clearest records of the ancient dying. The Karoo Basin, as geologists call it, is a place of flat-topped ridges and pale, layered stone. Walk across it slowly, and you walk through millions of years. Each band of rock is a thin page in a very long book, and somewhere in the middle of that book, the writing changes. The creatures that filled the pages above are not the same as the ones below. The Karoo is one of the few places on Earth where the land record of the Permian-Triassic boundary is so complete. Most extinction evidence comes from old sea floors, now lifted up as limestone cliffs. But here, in this quiet stretch of southern Africa, the story is written in river mud and floodplain soil. The animals preserved are land animals. Strange, sturdy beasts with stout legs and broad skulls. Their bones lie tucked in the rock like sleeping shapes. Above the boundary, most of those shapes are simply gone. What the Karoo whispers is something hard to fully grasp. It says that life on land collapsed too, not just life in the seas. The forests thinned, the rivers shifted their patterns, the plant eaters dwindled, and the meat eaters that fed on them dwindled with them. Whatever caused the great dying did not stay in the water. It moved through the air and across the soil and into the lungs of every breathing thing. Standing on that warm South African ground, it is hard not to think about how thin the layer of life truly is. The breathable air above us reaches only a few miles into the sky before it grows cold and empty. The soil beneath our feet, where roots and worms and small creatures live, is rarely more than a few feet deep. Between those two thin layers, almost everything we know exists. The seas add a little more thickness, but even the deepest ocean is shallow compared to the size of the planet. Life, in the end, is a faint skin on a great stone ball. The Permian collapse may have shown just how fragile that skin can be. If the volcanoes in Siberia changed the air enough, adding carbon dioxide, sulfur, and other gases, the whole delicate system tilted. Warmer air meant warmer oceans. Warmer oceans held less oxygen. Less oxygen meant suffocation for sea creatures. The carbon dioxide also made the rain more acidic, which damaged the forests, which fed back into the air, which warmed the planet further. One change leaned on the next, and the next leaned on the one after that. It is a sobering thought, and yet the evidence is still being read. Some researchers believe the tipping point was the ocean chemistry itself, with sulfur-rich waters rising up and poisoning the surface. Others suspect that the air alone was enough, that the warming and the acid rain together undid the land before the seas finished their slow change. The third view holds that no single trigger crossed the line, and that the whole system simply lost its balance in many small ways at once. The Karoo rocks, with their faded bones, cannot quite tell us which view is right. There is also the deeper question of why Earth is habitable at all. The distance from the sun is just right. Closer, and the oceans would boil away. Farther, and they would freeze solid. The atmosphere holds in just enough warmth, without holding in too much. The magnetic field, made by the slow churning of the iron core, deflects the harsh particles streaming from the sun. The crust is thick enough to be stable, yet thin enough to let heat escape. Every part of this works in quiet cooperation with every other part. Change one thing too much, and the rest may follow. The Permian extinction is, in some sense, a record of what happens when that cooperation breaks down. Whether the break came from below, from the great Siberian eruptions, or from above, in the form of changed skies, or from within the seas themselves, the result was the same. The thin skin of life grew thinner still. Most of it did not survive, and yet some did. The Karoo rocks above the boundary still hold bones. New shapes appear, smaller and stranger, but alive. The fragile system bent almost to breaking, and then it held. Why it held and how close the line truly came, the rocks of South Africa keep mostly to themselves. They lie quiet in the sun, waiting for the next careful hand to turn another page. There is a thin line in the rocks of the world that has puzzled geologists for over a century. It is sometimes only a few centimeters thick, sometimes it is barely visible at all. In a quiet canyon in southern China, in a cliff face in the Italian Alps, in a road cut in Iran, this line marks the boundary between the Permian and the Triassic. Above it, the world is empty. Below it, the world is full. And the rock itself, that strange narrow band, holds clues that scientists still cannot fully read. In some places, the boundary layer is a soft grey clay. In other places, it is a band of darker mudstone, streaked with the faint shadows of ash. In a few rare sites, it shines with tiny crystals, or carries a strange pulse of certain elements that geologists test for in their labs. Each of these features should help tell the story of what happened, and each of them, in its own way, refuses to give a single clear answer. One of the deepest puzzles is the chemistry of the boundary itself, the ratio of carbon isotopes, different forms of the same element that act like fingerprints, shifts sharply across this thin layer. Something flooded the ancient air and water with a huge pulse of light carbon. One theory points to the Siberian eruptions, burning through ancient coal beds and belching that carbon into the sky. Another theory wonders whether frozen pockets of methane on the seafloor melted suddenly, releasing their gas in a vast underwater burp. A third idea suggests the dying biosphere itself rotted in such quantity that the rotting changed the chemistry of the planet. All three may have happened. None of them, on its own, explains everything the rocks record. Then there is the puzzle of the timing. In some boundary sections, the extinction looks abrupt, almost a single page turn in stone. In other sections, the same boundary seems to spread across several layers, suggesting a slow unraveling over tens or even hundreds of thousands of years. Geologists argue gently about whether these differences are real or whether they come from how the sediments piled up in different places. A river delta records time differently than a deep ocean basin. The question of how fast life vanished may depend on which page of the planet you choose to read. The boundary layer also hides odd microscopic clues. In certain sites, scientists have found tiny grains of soot, suggesting widespread burning of forests or coal. In others, they have found grains of mineral that some researchers interpret as signs of an impact from space, though other researchers disagree about what those grains really mean. There are reports of strange fullerene molecules, of metal anomalies, of altered crystals. Each report sparks debate. Each piece of evidence is tested, retested, and sometimes withdrawn. The boundary is a place where careful science meets honest uncertainty, and where the next clean answer never quite arrives. Even the color of the layer varies in ways that puzzle the eye. In one quiet outcrop, the rock just below the boundary is a pale limestone, full of tiny fossil shells. Above the boundary, the rock turns dark and lifeless, almost featureless, before slowly regaining texture much higher up. Walking your hand across this surface, you can feel the change. The grain of the stone shifts. The world it records shifts with it, and no one fully agrees on why the dark, quiet rock above stayed quiet for so long. There is also the question of the boundary's missing pieces. In many places around the world, the rock layers right at this moment are simply gone. Either they never formed, or they eroded away long ago. This means the most important pages of the story have been torn out at exactly the moments scientists most want to read. To rebuild, The sequence, geologists must compare scattered sections from many continents, matching chemical fingerprints and microscopic fossils, trying to stitch a torn book back into something readable. What remains unsolved is not whether the extinction happened. The extinction is written everywhere. What remains unsolved is the exact recipe, the order of ingredients, the relative weight of each cause, the way one trigger may have led to another in a long, quiet cascade. The boundary layer is the crime scene, and it is both rich with evidence and stubborn with silence. Perhaps that is what makes it so compelling. The thin grey seam in the rock is one of the most studied surfaces on Earth, and yet it still holds back its secrets. Researchers return to it generation after generation, with new instruments, new ideas, new patience. The boundary waits. It has waited 250 million years. It seems content to wait a little longer. Far to the south, beneath kilometers of ice, there is a continent that once was green, Antarctica. Today is a vast white sheet, silent and cold. Its rocks hidden under glaciers that have crept across the land for millions of years. But beneath that ice, locked in stone, lies one of the most important fossil records of the great Permian dying. And much of it has never been seen by human eyes. In the few places where the ice pulls back, the bones of an older world rise into the wind. Geologists have walked the dark cliffs of the Transantarctic Mountains and found the remains of leafy forests, river deltas, and small four-legged animals that once breathed warm Permian air. These rocks tell a story of a southern world that was not yet frozen. They tell of swamps full of seed ferns, of slow rivers winding through wide plains, of creatures the size of small dogs sheltering in burrows. And then, in a thin band of stone, the story breaks. Above that band, the forests are gone. The burrows are empty. The rivers change shape as they did across the rest of the planet. Antarctica, in its own quiet way, kept the same terrible record. It lies in Siberia and South Africa and China. But here, the record is buried under one of the thickest ice sheets on Earth, and almost all of it remains unread. This is what makes the southern continent so interesting to those who study the Great Extinction. Most of Antarctica's Permian rocks are inaccessible. They lie beneath kilometers of frozen water that has not melted in tens of millions of years. Only thin strips of stone are exposed along the edges of mountain ranges, and at the coasts, the rest waits in darkness, untouched, holding fossils that no living person has ever held. What might be hidden there is the open question. One possibility is that Antarctica preserves refugia, small protected pockets where life held on while the rest of the world suffered. The southern latitudes may have been cooler during the worst of the volcanic warming, offering shelter to creatures that could not survive nearer the equator. If that is true, then somewhere beneath the ice, there could be fossils showing how certain lineages slipped through the bottleneck. The bones of survivors, the roots of plants that quietly outlasted the catastrophe. Another possibility is the opposite. Some researchers wonder if the southern hemisphere was struck just as hard, or harder, than the north. The few exposed rocks already show severe loss of forest cover. The recovery, when it came, seems slow and patchy. If Antarctica was not a refuge, then the hidden fossils may instead reveal how complete the collapse really was. Even at the furthest ends of the world, both views remain on the table, and the ice is not giving up its answer quickly. There are also the rocks of the deep interior, places no field team has ever visited. Beneath the high plateau of East Antarctica, beneath ice 3 or 4 kilometers thick, there are buried basins of Permian sediment. Within those basins, Somewhere are the pages of the extinction story, written in southern stone. Whether they will ever be read is a question for the next century or the next 1,000 years. The future of this mystery depends partly on what the ice itself decides to do. In a warming world, the edges of Antarctica are slowly changing. New rock is being exposed each decade as glaciers retreat in certain regions. Field teams visit these freshly uncovered cliffs and sometimes find fossils that have been hidden since long before humans existed. Each new outcrop is a small window into the deep past. Each one might hold a clue that shifts the debate. Imagine, far in the future, a world in which much of the ice has changed shape and the Permian rocks of Antarctica lie open to the wind. Imagine what a patient researcher might find walking those cold valleys. A slab of stone with the print of a leaf no living botanist has seen. The jaw of a small creature whose lineage left no other trace. Such finds could reshape the story entirely. Or they could simply confirm what the northern rocks already whisper. For now, the southern continent keeps its secrets. The bones rest in the dark. The leaves wait, pressed flat between layers of sediment, in a silence that has lasted 250 million years. And somewhere among them, perhaps, is the missing piece of the puzzle. The single fossil that would tilt the great question, one way or the other. We do not know if we will ever find it. The ice, for now, is patient, and so the mystery sleeps with it. Step back now. Step back as far as your quiet mind will let you, beyond the rocks of Siberia, beyond the warm, shallow seas of the Permian, beyond even the round blue shape of our planet, turning slowly in the dark. From far enough away, the story of this extinction becomes part of something much older and much larger. It becomes part of the long story of carbon itself. Every living thing on Earth is built around carbon atoms, the wood of a tree, the shell of a clam, the bones in your hand, the dark seams of coal pressed deep into ancient stone. Carbon is the patient thread that ties all life together, and those carbon atoms did not begin on Earth. They were made inside stars, long before our world existed. Old stars, burning steadily, fused lighter elements into carbon in their hot cores. When those stars died, they scattered that carbon across the dark. Some of it gathered, over billions of years, into the cloud that became our sun and our planet. So, the carbon in a Permian fern is the same carbon, in a sense, as the carbon in your breath tonight. It has only moved through different forms, into leaves, into soil, into the bodies of small creatures with strange flat eyes, into limestone reefs, into the lungs of the lonely reptile walking through the ash. The Permian extinction, seen from this wide view, was not the end of carbon. It was a violent reshuffling of where the carbon lived. When the Siberian traps poured out their lava, they cooked vast deposits of buried carbon and released them into the sky as carbon dioxide and methane. Carbon that had been resting quietly in the ground for ages suddenly entered the air and the sea. The oceans absorbed some of it and grew slowly sour. The atmosphere held more of it and grew slowly warmer. The forests that had pulled carbon out of the air for hundreds of millions of years collapsed and stopped pulling. The balance tipped and life paid the price. What survived rebuilt the balance slowly in new forms. New trees grew, new reefs formed, new creatures learned to breathe the changed air. The carbon kept moving. It always keeps moving. It is moving right now. Through the leaves outside your window, through the soil beneath the streets, through the slow breath of the deep ocean, through your own chest as you lie still. There is something quietly humbling in this. The atoms that built the trilobite are not gone. They were taken apart and used again. Perhaps some of them are in a blade of grass tonight. Perhaps some are in a whale, sleeping in the cold dark of the North Atlantic. Perhaps some are in you. We are, in a real and literal sense, made of the remade pieces of older worlds. What the Permian extinction may teach us is not a single sharp lesson. The mystery, after all, remains open. We still do not know exactly what tipped the balance, or in what order, or how quickly. We may never know with full certainty, but the rocks do whisper one steady thing. They whisper that the systems of Earth are connected. The air speaks to the sea, the forests speak to the sky, the volcanoes speak to the plankton. Carbon moves between them all, in long, slow loops that take millions of years to complete. When one loop is pushed hard enough, the others answer. Whether the push that drove the Permian world to the edge came mostly from volcanoes, or partly from a distant impact, or from rotting seas, or from some quieter cause we have not yet imagined, the deep pattern looks the same. Life endured. Life always endures, in some form. But the shape of life changed forever. The creatures who lived before were not the creatures who came after. You are part of that long, patient story. The calcium in your bones was forged inside dying stars and scattered across the dark, just like the carbon. The iron in your blood was made the same way. You are a brief, warm gathering of very old atoms, resting on a planet that has been gathering and scattering atoms for 4.5 billion years. The trilobite was the same. The fern was the same. The lonely reptile in the ash was the same. From this far away, the extinction is not only a tragedy, it is also a turning, one of many in the slow song of Earth. The song continues. The carbon keeps moving. The stars keep making more. And on a quiet night, one of those tiny gatherings of ancient atoms lies still in the dark and wonders. And so we come to the end of our long, quiet walk through deep time. 23 pieces of an ancient puzzle, each one a small candle held up to the dark. The Siberian traps and their endless rivers of lava, the sour seas, the silent forests, the strange recovery world where fungi rose and reptiles wandered through ash, the coal that stopped forming, the reefs that fell quiet for 10 million years, the fossils still locked in Antarctic stone, waiting for someone to find them. And after all of that, the central question stays where we found it. We still do not know exactly what happened at the end of the Permian. We do not know the precise order of the blows. We do not know whether the Siberian eruptions did all the damage on their own, or whether some other force, an impact, a release of frozen methane, a chain reaction in the oceans, pushed the world over the edge. We do not know why some small plain creatures lived while bright, beautiful ones vanished. The evidence we have is real. It is just not yet enough. There is a kind of peace in that. Not every question needs to be answered tonight. Some questions are better held lightly, the way you might hold a smooth stone in your palm before setting it down by the bed. The stone does not need to be solved. It only needs to be felt. Picture the Earth now as it is in this moment, a blue and white sphere turning slowly in the dark, oceans moving in long, patient tides, clouds drifting in soft spirals across the seas. On the night side, the land is dim and quiet, dotted with the warm pinprick lights of sleeping cities. Forests breathe slowly in the dark. Rivers find their way to the sea, just as they have for billions of years, pausing only when ice or stone tells them to wait. Somewhere over a wide ocean, the moon is bright on the water. The surface shines like beaten silver, gently rising and falling. A pale path of light reaches from the horizon all the way to the shore. No one is watching it. The waves do not need an audience. They have been doing this since long before the Permian, and they will keep doing it long after tonight is forgotten. In the deserts, the air is cool and still. Sand that was once the floor of a Permian sea lies quiet under the stars. In the mountains, snow falls in slow, soft sheets onto stones that remember being something else entirely. In the deep forests, a single drop of water slides from one leaf to another, then to the moss below. The earth keeps its small motions going all night in every place at once. You are part of that quiet motion, your breath, rising and falling, slow and even. Your heart beating its old, patient rhythm, the same rhythm that has run through every animal that ever lived on this world, the same rhythm that ran through the little burrowing creatures who slept through the worst night in Earth's history and woke up and walked on and became the ancestors of nearly everything warm and breathing today, including you. The mystery of the great dying does not need to be solved before you sleep. It has waited 250 million years. It can wait one more night. Perhaps in your lifetime, someone will find the missing piece, a perfect layer of stone in some quiet hillside, a chemical fingerprint no one expected, a fossil that finally tells the rest of the story. Perhaps not. Perhaps the answer will come slowly, the way most truths about this old planet come, in small pieces, gathered by patient hands over many years. For tonight, it is enough to know that the earth has survived its worst day and kept turning and grown forests again, and reefs and rivers and us. It is enough to know that the same stones that hold the record of that ancient ending are still here, still waiting, still willing to be read. It is enough to lie in the dark and feel the slow weight of deep time, and to know that you are held inside it, small and warm and safe. The planet is breathing, the oceans are resting, the stars are turning slowly above the clouds, and the great old question of the Permian is settling back into its bed of stone, content to be wondered about tomorrow, and the night after, and the night after that. Rest now. The earth will keep its watch. Subscribe for a brand new earth topic every night. One tap and something wonderful is waiting for you tomorrow. Sweet dreams.